Bismillah ar-Rahman ar-Rahim. Now, after we talk about the indefinite integral, if you remember, we defined the indefinite integral to be the set of all antiderivatives of a given function. So, if we have the integral of small f of x, we said this is just capital F of x plus constant, where we have the derivative of the capital F is equal to f of x. And our target now is to improve our skills in finding antiderivatives. One interesting rule that will help us to find antiderivatives is called the substitution rule. The substitution rule. What is the substitution rule? Simply it says if you have u is equal to g of x is differentiable function whose range is an interval I, and we have another function called f that is continuous over the range on I, then we have the following. That if we have an integral of f g of x g prime of x dx, that is simply equal to f of u du. What the substitution rule says actually is the following, that if you have such a type of integrals, then easily you can make a substitution u equal to g of x. Since this function is differentiable, you can calculate the differential du, which is g prime of x dx. So simply it says you can always replace composite of functions by the following substitution. So we have g prime of x dx, this is only du, and you have f of g of x, that is f of u. So you start with the relatively complicated integral, not easy integral in the shape, and you are getting a better shape of that integral that may help in solving the new integral. Okay, how to apply this technique, or how to apply this rule, or how to apply this procedure, we will have some exercises now to see how to apply the substitution rule. Okay, I start with a simple one. I start with this simple integral that says integrate x cubed cosine x to the power 4 plus 2 dx. Our target to find all antiderivatives of this function. Okay, we try to think. If we make x to the 4 plus 2 equal to u, for example, do we have its derivative, or at least a constant multiple of its derivative? The answer is yes. If we let u equal to x to the power 4 plus 2, you can see here x to the 4 plus 2 plays the role of g of x here, f of g of x, so we have cosine of g of x, something like this. What is the differential here, du equal to? Du simply is the derivative of this times dx, so that is 4x cubed multiplied by dx. Now let us go back to our integral. Our integral says you need to integrate this, which is x cubed cosine x to the 4 plus 2 dx. I will not substitute directly, rather I will simplify for us. So this is x cubed cosine of x to the 4 plus 2, and this is dx. Now what I need here, I need 4x cubed dx. Okay, I have x cubed, I have dx here. What is missing? Only the number 4, but always I can multiply by a constant, I divide by the same constant if that constant is not equal to 0. I am ready now to convert the integral into another form that will be equal to, look, I have 1 over 4 integral of, look, 4x cubed dx, this is nothing but du. So what do we have here? We have du, and we have what? We have cosine of our substitution here, x to the 4 plus 2, which is equal to u. Now look for the two integrals, the first one and the last one. It seems that the last one we get is much easier than the previous one. Now looking for the new integral and the previous one, you can easily see that the new integral is much easier than the previous one. Now what is the integral of cosine? As we did before, the integral of cosine is just sine of u plus a constant of integration. Now we are integrating with respect to x, and the final answer is getting in terms of u. We need to go back and resubstitute the value of u, which is x to the 4 plus 2. So we're substituting back, we get the answer for the original integral we have. So we can conclude now that the integral of x cubed cosine of x to the power 4 plus 2 dx is nothing but the final answer here, which is 1 over 4 times sine of u, but u is x to the power 4 plus 2. So the final answer will be x to the power 4 plus 2, all plus constant c. So you see the idea of substitution. We start with an integral, we make a substitution, we make the integral simpler, then we integrate and go back and substitute to get the original integral. That's mainly the idea of substitution. We will do only more exercises to see how to apply this strategy in different type of questions. Now, what is the next one? Let us see another exercise here. Number 2, for instance, says evaluate the following integral, that is x divided by square root of, we have 1 minus 4x squared dx. Okay, that is another question where we can apply the substitution rule. Okay, we have choices for u. Maybe someone will say I will take u equal to x, but is it helpful or not? Someone else will say, okay, I will take u equal to 1 minus 4x squared. You need to try and see the new shape of the integral. If it is better, then it's okay. Otherwise, you need to change your mind. Okay, a clear one here, we can say that let u equal to 1 minus 4x squared. Why? I'm thinking like this, because I have the derivative of this, or a constant multiple of the derivative. The derivative of this function is minus 8 multiplied by x. I have x here, so I can easily multiply by minus 8, divide by minus 8, so things will be smooth. Okay, what is the differential du equal to? What is du? Du is the derivative of this, that is minus 8x dx. Let us see if we can get a better form than the original integral we have. Okay, I need minus 8x dx. Do we have it here? We have x dx, so we can easily modify it before we go and substitute. I need minus 8x dx. That's not a big deal. I can multiply by minus 8, so I have minus 8x dx divided by whatever we have here, square root of 1 minus 4x squared. Okay, but I multiplied it by minus 8, so I need to divide by minus 8 outside. So I have an equivalent expression. Let us look at it now in terms of u. So I have minus 1 over 8 integral of, yes, I have minus 8x dx, that is nothing but du, divided by, this, all of the denominator here will be only radical of u. Comparing the original integral and the new integral we get, this is much easier than the previous one. And this is the beauty of the substitution. We are solving the same thing, equivalent expressions, but one of them is looking much better than the previous one. So that's the idea of substitution. Now, how to integrate du over radical u? That is a simple one. You have minus 1 over 8. If you like, you can write it as u to the power minus 1/2 du. Then use the formulas we had before. That's minus 1 over 8 times. We need to add just 1 to the exponent and divide by the new exponent. So that will be u to the power minus 1/2 plus 1. That is equal to 1/2. Divided by 1/2, it means you are multiplying by 2. All of this, you need to add to it the constant of integration. So what is the final answer then? The final answer will be minus 1 over 8 times 2. That is minus 1 over 4. U to the power 1/2. That is radical of u. What is u? U is the expression here. We have 1 minus 4x squared. 1 minus 4x squared. Adding to this, a constant of integration. So this is the main idea again for the substitution. It is a technique that moves a more complicated integral into a simpler integral. We need to practice more because this is a very important skill we need to learn in integration, because we are recovering the function, the antiderivative of a function, by using different techniques. And this is one of the most important techniques we have, which is called substitution rule. We will see more exercises now. Now let us see this nice exercise here that says, it is very simple exercise, but it is very beautiful exercise. The integral of sine x cosine x dx. Now someone will say, is the choice of u of x unique or not? Let us look for the exercise here. Someone will say, I look at this as maybe this is u, cosine is u, and the derivative is minus sine u. That's okay. Someone else will say, no, I will look at it as this is u and this is du. Let us see what will happen if we choose different choices for u of x. Okay. If we say I will let u equal to sine of x, okay? What will be du? Du will be equal to the derivative of sine, that is cosine of x dx. Okay, going back to the integral we have, this is the new form of the integral. I have cosine x dx, this is du. So what do we have here is just u du, and that is equal to u squared over 2 plus constant of integration. Okay, fine, this is equal to, what is u squared? It is sine squared. Sine squared of x over 2 plus a constant of integration c. And this is a correct answer, because if you differentiate sine squared of x over 2 plus c, the derivative of this will give you what? The derivative will give you 2 sine of x cosine of x, that is the derivative of sine squared, divided by 2 plus 0, because the derivative of c. Clearly here we have sine cosine, which is the integrand. So yes, this is an antiderivative, adding a c, that will give me all antiderivatives. Now, what will happen if we choose another choice for u of x? Someone will say, okay, instead of choosing u equal to sine of x, I will choose, this is another way to do it, okay? I will let u equal to cosine of x instead of sine. If you choose u to be cosine of x, what will happen here? You have du is equal to minus sine of x dx. So going back to the integral we have, the integral will be what? I need minus sine x dx, so I will multiply by a minus sign here, a minus sign outside, so I will have minus, I have a minus sign here, a minus sign here, so minus sine x dx, this is du. So what do we have is minus what? Cosine is equal to u, so it is minus u du. What is the final answer then? It will be minus u squared over 2 plus constant c. Okay, what is this? It is minus cosine squared of x divided by 2 plus constant c. Is this one a correct answer? The answer is yes. You can check that. If you differentiate this, what do you get? What is the derivative d by dx of this expression minus cosine squared of x divided by 2 plus constant c? Okay, what is the derivative of cosine squared? Using the chain rule, we have minus, we have 2 cosine of x to the power 1 times the derivative of cosine, which is minus sine. So this is plus, and this is sine of x divided by 2. Derivative of c is equal to 0. Again, we are recovering the function. Yes, at the end of the day, we have different form of the final answer. But both of them are correct. Maybe someone else will say, no, I don't choose u to be sine. I don't choose it to be cosine. What I will do is the following. This is, let's say, method number 3. So we have different ways to think about the same exercise. Now, someone say, okay, I look at this sine, cosine, that was our original question like this. This is what we have at the beginning here. This is what we have. So what I will do, I remember the double angle identity for sine. So if I multiply it by 2 here, divide by 2 here, this is what I will get. Our integral will be equal to 1/2 times 2 sine of x cosine of x dx. Okay, but what is this? 2 sine cosine, this is sine of the double angle. So that is equal to 1/2 integral of, this is nothing but sine of 2x dx. Okay, so what is the final answer here? Using the formula we have minus, this is 1 over 2 cosine, so that will be 1 over 4 integral of sine, that is cosine of 2x plus constant c. The minus came from the integral of sine, and we have 1/2 here, we have 1/2 here, the multiplication was 1 over 4. Again, if we differentiate this, we get the same integrand. So all these kind of substitutions are working fine. I can do it by this substitution, I can do it by this substitution. I may use identities to reform the question and solve it. At the end, we need antiderivatives. We need the correct form of one antiderivative plus some constant of integration. So the choice of u is not unique. You may start with a choice of u, and someone else can choose another one. And both of you will reach the same, not the same answer, but a correct answer. Okay, we'll see more ideas about the substitution rule in the coming exercises. Okay, let us see more exercises about substitution. So this is number 3 that clarified for us that yes, we may have different thinking and we end up with correct answer. No problem. Integral of, okay, integral of, we have here dt, we are integrating with respect to t the following. We have cosine squared of t square root of, this is 1 plus tangent of t. Okay. What is a suggestion for you? You may have different trial to reach the answer, but here a very clear one is 1 plus tangent. You may take 1 plus tangent. You may take u equal to tangent. It's up to you. But one way to do it is the following. We can do the following substitution. We can make the following substitution. We make u equal to 1 plus tangent of t. Now someone will say, how do you know that it is equal to u? Nobody knows. You need to think, do we have the derivative of this? What is the derivative of 1 plus tangent? That is secant squared. Okay. Do we have secant squared? Yes, but it is written in different form. 1 over cosine squared is secant squared. So it seems that this will work fine. You try and see what is happening in the second line. If the second line is moving smoothly, then what you are done is correct. So what should we do now? Go ahead and calculate this. du. What is du? It is the derivative of this. That is secant squared of t dt. Okay. Again, going back to the integral we have, what should we do here is just reform it. So what do we have here is the following. 1 over cosine squared, that is nothing but secant squared of t dt, if you like, divided by what? Divided by square root of 1 plus tangent of t. I did nothing here except that I reformed the integrand I have in another shape. Okay. What else now? I make the substitution. Secant squared t dt, that is du. So it is just du divided by, what is this? Square root of u, or u to the power 1/2. Okay, what is it equal to? In other words, it is u to the power minus 1/2 times du. Okay. What is it equal to now? This is equal to u to the power minus 1/2. You add 1, you get u to the power 1/2 divided by 2, divided by 1/2. So you are multiplying by 2. So that will give you 2 radical of u plus constant c, which is actually 2 square root of the substitution we made, which is 1 plus tangent of t plus constant of integration. That is another exercise to show the beauty of substitution rule. We will see more exercises also. Okay. Okay, now the next 2 exercises will illustrate for us that sometimes before we make a substitution, we need to do some simplification. It is always recommended that if we can simplify the integrand, we simplified it before we go and make a substitution. Let us see this. Look here, we have e to the power x cubed plus 2 ln x dx. For the first log, there is no clear substitution. But if we think about the following integral here, let us call it I equal to, I will call this is I, so this is our integral. Now I will reform the integrand. I have e and ln. So I always remember this. If I have e to the power ln of x, this is always equal to x if we have a positive number x. Okay, a positive real number. So e to the ln x equal to x if x greater than 0. We can always use this property to simplify whenever we have e to the power ln or ln of e. Always these are inverse of each other. So what do we have here? I can rewrite this one as e to the power x cubed multiplied by e to the power 2 ln of x dx. I'm using the properties of the exponentials. Okay. So if you multiply here, you need to add exponents. So you go back to the original shape we have. Good. Now what about the second one here? I have e to the power 2 ln of x. I can take this one inside as exponents. So what do we have? I will have e to the power x cubed times e to the power ln of what? X squared dx. Since we have ln of x here to make this integrand to make sense, we're supposed to have x greater than 0. So the domain from the beginning, we have x greater than 0. Okay, so if x greater than 0, then of course x squared is greater than 0. So what do we have here is the following. We have the integral of x squared e to the power x cubed dx. Now, we did not make a substitution yet. We just simplified it until we reach the last step, which is much better than the previous one. I mean the original one. So now someone can think about a substitution. Clearly here, if we make u equal to x cubed, then we have the derivative of this. The derivative is du, or the differential is du equal to 3x squared multiplied by dx. Okay. When I said I have the derivative, I mean by that a constant multiple of the derivative. It's not always ready that we have the derivative, but here we have x squared dx, x squared dx. We are looking only for the 3. That is a constant. Always we can multiply, divide by the same constant if it is not 0. Okay. Here I can reform the integral now to be equal to, I need 3 here, so I will divide by 3 outside. I will multiply by 3 inside, so I have 3x squared dx, that is du. And here I have e to the power u, and simply this is equal to 1 over 3 e to the power u plus constant of integration. Now, what is e to the power u? U is equal to x cubed, so the final answer is 1/3 e to the power x cubed plus a constant of integration. So, again, before we make a substitution, sometimes it is recommended to simplify the integrand we have, especially if the substitution is not too clear for us. We need to do some algebra, we need to do some simplification before we go and make a substitution. Another example that will illustrate this idea also is this expression here that says integrate x cubed plus 2x squared plus x plus 2 divided by x to the 4 minus 3x squared minus 4 dx. From the first look, we have no clear substitution because I don't have the derivative of this, and also I don't have the derivative of that one, so there is no clear substitution for you. So what should we do? We think about the question in terms of algebra. Can we do some algebraic steps here to simplify? And the answer, we try and see. We try and see what will happen here. So one thinking here, one way to move from the original question here is to factor out things. So what do we have here? X to the 4 minus 3x squared minus 4. This can be factored out into what? Into x squared minus 4 times what? X squared plus 1. We have 1 times minus 4 is minus 4, x squared, that is x to the 4. I have x squared minus 4x squared, that is minus 3x squared. That is one thing here. Looking for the numerator 1, 2, 3, 4 terms, so we can do factoring by grouping. For example, I can take x squared from the first 2 terms. I will end up with x plus 2, okay? Then I have x plus 2 here. So this is one step in the factorization because now I have x plus 2, x plus 2. So it seems what I did is working fine. So I will do another step here. I will take x plus 2 to be a common factor from the numerator here. So I have x squared plus 1 divided by, now this is difference of 2 squares. I can leave it x squared minus 4. I can factor it into x minus 2, which is better, times x plus 2, and I have x squared plus 1. You see the beauty of algebra here that simplify the question. You see x squared plus 1 is the same as x squared plus 1, so I can cancel it here. I have x plus 2, I have x plus 2, they will be cancelled out. So what do we have at the end is the integral of 1 over x minus 2 dx, and simply by using the formulas we have, this is equal to logarithm of x minus 2, of course, absolute value plus constant of integration. So in conclusion, we can say that sometimes before we make a substitution, or if the substitution is not so clear for us, we need to do some algebra, we need to do some simplification, then we do the substitution, and then we solve the question. Okay, we'll see more questions only. This is the idea of the substitution, but just to see more exercises, we will see the next exercise now, which is very interesting also. Another idea about substitution. The idea is the same, but you have different shapes, you have different type of functions, you have different tricky points, then you need to handle, you need to think about, you need to try, you need to practice. So we will do more exercises only. Okay. So this is the 7th question we do, that integration of square root of 1 plus x to the squared, sorry, 1 plus x squared, and this is x to the 5, this is dx. Now, what is the substitution we need to do? Okay, we have no problem with x to the 5, but the problem here that we cannot multiply this inside. I mean, we cannot say 1 plus x squared to the power 1/2. This is not equal to. I cannot distribute the radical. I cannot say this is radical 1 plus radical of x squared. This is totally wrong, isn't it? We cannot distribute radical over summation. So, the expression that creates the difficulty here is the radicand, 1 plus x squared. So, if we can make a substitution, make this one as a single term, let u equal to 1 plus x squared, then we may simplify the question. Let us think and see. What is du? Du is 2x dx. Now looking back for the question we have, do we have 2x dx? It is not a big deal for the constant here. Always we can multiply and divide by that constant. So let us look for the integral in the following form. I need to separate x dx, so what I will do, I will go back and write it as 1 plus x squared. I will separate x, so that will give me x to the power 4 x dx. This is what I need, okay? I need 2 somewhere here, so I will multiply by 2 and I will divide by 2, okay? Then what I will do, I will think about the rest. Okay, I have 2x dx, this is du, fine. Radical of 1 plus x squared, this is u, so this is u to the power 1/2. But what is also x to the power 4? Clearly from here we can get x squared equal to what? U minus 1. So can we get x to the power 4? Yes, we have x to the power 4 is equal to u minus 1 all squared. Let us look for the new shape now and see if it is easier or not. So what I will do, I will replace this one by u, so this will be u to the power 1/2. What about x to the power 4? X to the power 4 is u minus 1 all squared. What about 2x dx? That is du. Now, this is our original question, and this is the new shape of that question. Yes, we are removing the problem now, because here what do we have is 1/2 times what? We can open the squared now. Before we cannot distribute the exponent, but now what do we have here is u to the power 1/2, which is a single term, times expanding this will give us u squared minus 2u plus 1 du. So we are converting by multiplying now the term u to the power 1/2 for the 3 terms here using the distribution law. U to the power 1/2 times u squared, u to the power 1/2 times 2u, u to the power 1/2 times 1. We will end up with very elementary type of functions, okay, that can be integrated easily. So yes, this substitution helped us to convert a relatively, let us say, not clear integral into some basic functions that we can integrate using formulas. So what is the new step here we have as a continuation of the solution of this exercise? We will have the following expression here. So this implies, okay, let us remove this one also. So this implies our integral now is equal to 1/2 times the integral of, now let us multiply. You have u to the power 1/2 times u squared, that is u to the power 5 over 2. We are not yet integrating. We are just simplifying until now. Minus 2, we have u to the power 1. U to the power 1/2, that is u to the power 3/2. Okay? And then we have 1 times u to the power 1/2. That will give me u to the power 1/2. And then we integrate everything here with respect to u. Okay, fine. This is equal to 1/2 times, now, you have u to the power 5/2. You integrate, you get u to the power 7/2, adding 1 and dividing by 7/2. That is multiplying 2/7. Minus 2 times u to the power 5/2 times 2/5. I am dividing by 5/2, so I am multiplying by 2/5. Similarly, here we have u to the power 3/2 divided by 3/2. It means multiplying by 2/3. All of this adding constant of integration. Then we simplify. The final answer will be 1/2 times 2, that is 1. So it is 1/7. U to the power 7/2. What is u? U is 1 plus x squared. So that is 1 plus x squared to the power 7/2. Minus, we have 1/2. We'll cancel with this. So what do we have is minus 2/5 times 1 plus x squared to the power 5/2. And finally, we have plus 1/3 because we have 1/2 with the 2 will cancel out. You have 1/3, 1 plus x squared to the power 3/2 plus a constant of integration. So that's an idea about antiderivatives using substitution rule. Of course, you can simplify more than this, but this is a final answer, or let us say a set of all antiderivatives of the original integrand. Okay, this clarifies the idea of substitution. What I will add now is just how to deal with definite integrals if we have, and the substitution rule. How to, calculate some definite integrals, the substitution rule, together with definite integrals that will give us solutions of different type of definite integrals by using substitution rules. So I'll give you some ideas about this. Okay, let us see now the first example, how the substitution method will be used to solve definite integrals. Okay, how to read this one? The question says evaluate the integral from 0 to 1 of radical 1 plus 7x dx. When you look for this, look for the lower point and the upper limit here, the lower limit and the upper limit. It says that x is moving from 0 to 1. How to simplify this? How to find another form of the integral which is simpler? And this is the idea of substitution. You start with an integral, you make a substitution, that substitution will give you a simpler integral. Okay, so what is the substitution you can see here? Okay, we'll say let, for example, because we have problem with this, so I will say let u equal to what? 1 plus 7x. Now I need to replace everything with x in terms of what? In terms of u. So what is du? Du is equal to 7 times what? 7 times dx. Okay, so dx in other words is equal to, dx is du over what? Over 7. That is interesting. Now let's come to our integral. Let's call it I. Our integral, I is equal to what? I will start. This is 0 to 1. This is 0 to 1. Radical of what? 1 plus 7x dx. Now, changing everything now. I will change 1 plus 7x and I will insert u. So that is the integral of, it will be radical of u. I will replace dx. dx is du over 7. So it is, okay, I can write it here. It is du over 7. It's okay. But don't forget to change also the boundary points, because the boundary is written here are for x variable, not for the u variable. So what should I do? I will come to the first limit here, which is the 0. And I will ask myself, if x equal to 0, u equal to what? If x equal to 0, this is 7 times 0, which is 0 plus 1. So that will give me u is equal to 1 in the lower limit here. the same way. If x equal to 1, u equal to what? X equal to 1, so this is 7 times 1 is 7, plus 1, that is equal to what? That's equal to 8. So this is the new form of the integral now. Integral from 0 to 1, radical 1 plus 7x dx is equivalent to integrating from 1 to 8, radical u du over 7. Okay, let us now do the calculation part. This is equal to, I will take 1 over 7 outside, so this is 1 over 7. Then I will integrate radical u. What is the integral of radical u? U to the power 1/2. That's it. U to the power 1/2 plus 1. That is 3 over 2. Divided by 3 over 2. So that is equal to what? 2 over 3. U to the power what? 3 over 2. It's actually u to the power 3 over 2 divided by 3 over 2. But you know, it will be 1 over 3 over 2. That is 2 over 3. And this need to be calculated from, evaluated from 1 to what? From 1 to 8. Okay. Now, if you allow me, I can take this one outside also. So this will be 2 over 21. And then I will evaluate at the first point, that is 8 to the power 3 over 2 minus at 1. This is equal to what? This is equal to 1. This is the answer, but you can simplify it more if you like. This is equal to 2 over 21. You can write this one as what? This is 8 to the power 3 over 2. So it is 8 radical of 8 minus 1. This is one way to write it down. You can simplify more also. Why this is 8 radical 8? What is 8 to the power 3 over 2? That is radical 8 to the power 3. And radical 8 to the power 3 is radical 8 times radical 8 times radical 8. 3 times. But this will give you 8. So it is 8 radical 8. Now, more simplification, if you like, you can do this also. Because still 8 is 4 by 2. I can take the 4 outside by 2. 2 times 8 will be what? 16 radical 2 minus 1. You can keep it this way. You can also multiply by the fraction outside and write it in another form. But this is the final answer. And this is how the substitution rule is used to solve definite integral. Okay, let me just make a comment here. Look, I will just write a solution and some notes about the solution. Some students, what they will do if you give them a question like this, they will say, okay, this is 0 to 1, this is 0 to 1, radical of, and then they will write 1 plus 7x dx. So, okay, I will make a substitution u, that is 1 plus 7x. When they come to substitute now, they will evaluate du, no problem. And they will say it is 7 times dx. Okay, but when they come to the integral, they will write like this. 0 to 1, radical u times du over 7. What is wrong here? What is wrong here? Okay, they change this to u. Also, they have changed dx into du over 7. But they forgot to change what? The boundary points. If you forget to change the boundary points, all your calculation will be what? Will be wrong. So again, I address in this point. If you change by using the substitution rule, you change everything, including what? Including the boundary points. It is not 0 to 1. It's supposed to be, as we did here, it says from 1 to what? 1 to 8. That is something you need to be careful about. Okay, let me show you another example. And the second example will be evaluate the following integral. Evaluate the second, let me call this one, if you like, part A. And the second one, let us call it part B. So again, part B says evaluate the integral from 0 to 1/2 sine inverse of x divided by radical of 1 minus x squared dx. Before I go to the second solution or the solution of the second example, I have another comment here. Some students said, okay, what happened if I remove the boundary points? Okay, I will remove the boundary points. Then I will say this is 1 over 7 times the integral of radical u du. So this is equal to 1 over 7 times what? 1 over 7 times, and I will integrate now. This will be u to the power 3 over 2 times 2 over 3. Okay. Plus constant of integration. I'm doing it as it is indefinite integral. And then I will write this one as 2 over 21. And then I will replace u by the value which is what? 1 plus 7x. So this will be 1 plus 7x to the power what? 3 over 2 plus what? A constant of integration. And then if someone asks me to evaluate this, I need only one function that is an antiderivative according to the fundamental theorem of calculus. I can take this one, 2 over 21, multiplied by 1 plus 7x, okay? All to the power 3 over 2, and then evaluate it from what? From 0 to 1. Is this one correct or not correct? This is perfectly alright. Perfectly alright. Because you change everything to u and you bring it back to x. Then you substitute the x values from 0 to 1. So this will give us the same answer as this one. And you can check it. You just substitute by 1. This will be 1 plus 7. That is 8 to the power 3 over 2. Minus at 0, this is equal to 1. Which is exactly this. 8 to the power 3 over 2 minus 1. So you have two options. Either you change everything, change the x, change the boundary points, evaluate, or you treat it as it is indefinite integral, try to find an antiderivative, and then at the end, substitute with the first boundary points. Okay, now I can come to the second exercise to do the same thing we did in this exercise. The exercise says evaluate from 0 to 1/2 sine inverse of x dx over radical 1 minus x squared. How to use substitution rule to find the answer? How to use substitution rule to find the answer? Clearly here, if you take u, if you let u equal to sine inverse of x, then du will be equal to what? The derivative of it will be just the differential is 1 over square root of 1 minus x squared what? dx. Now, I will use the first way to present the solution, or the first way to show how the solution goes to the final answer. I will call that integral I. Now I will come to the integral and I will change everything. Sine inverse of x, I will call it u. So this is u. 1 over square root 1 minus x squared dx, all of it is du. So if you allow me, this will be just u times du. What about the boundary points? Yeah, okay. At x equal to 0, x equal to 0, sine inverse of 0, that is equal to 0. I will change the boundary point. If x equal to 1/2, what is happening to you? It is sine inverse of 1/2. What is sine inverse of 1/2? What is sine inverse of 1/2? That is equal to what? Pi over 6. Why? Because sine pi over 6 is equal to 1/2, and pi over 6 is between minus pi over 2 and pi over 2. That's the definition of sine inverse. Okay, interesting. What is the answer then? Now you can see, we start with a little bit complicated integral. By using the substitution rule, it happened to be a very simple integral, but we need to use it carefully because we change also what? The boundary points. So that is u squared over 2 evaluated from 0 to pi over what? Over 6. So what is the final answer then? You substitute pi over 6, you have here what? You have pi squared, sorry, this is pi squared over 36, all divided by 2. So I will multiply here by 1/2. This is all multiplied by 2. I will take the 1/2 common factor. Minus, at 0, this is equal to 0 over 2, which is equal to 0. So what is the final answer? The final answer is pi squared over 72. So that is the solution of the second example. Now we discussed the indefinite integral and how the substitution rule is used to simplify integrals. Also we saw how to evaluate definite integrals by using substitution rules. What is next? The next point will be properties of definite integral, or one more property of definite integrals for a specific type of functions called even functions and odd functions. That will be discussed in the next point. Now, before we go to discuss the property of definite integral over special type of functions called even and odd functions, let me remind you what the meaning of these terminologies. So if we have y equal to f of x, if we have a function y equal to f of x, then when can we say that this function is even? The answer will be a function is said to be even if it satisfies the following condition. That is, f of minus x is equal to what? F of x. F of minus x is equal to f of x. What does it mean geometrically? F of minus x equal to f of x. It means the function is symmetric around the y-axis. Symmetric around the y-axis. Typical example. Y equal to x squared. Y equal to x squared is an even function because it is symmetric around the y-axis, and also if we replace x by minus x, the same function will be gained. So that is called an even function. What about the odd functions? When can we say that a function is odd? A function is said to be odd if it satisfies this. F of minus x is equal to what? Minus f of x. Geometrically, odd functions are symmetric around the origin. Typical example, y equal to x cubed. Y equal to x cubed, something like this, coming down, then it is symmetric around the origin. Okay, so y equal to x cubed, you can see now if you replace x by minus x, so f of minus x will be minus x cubed, and that is equal to minus x cubed, which is equal to minus f of x. In this case, we say y equal to x cubed is said to be an odd function. Coming now to the property. Let us see here. This nice remark says, assume that you have a continuous function over the closed interval minus a to a. So you have symmetry in the interval, minus a to a. Then, if f is an even function, then the integral from minus a to a f of x dx will be equal to twice the integral from 0 to a f of x dx. This sometimes simplifies the calculation. The second one, which is interesting also. If f is an odd function, if f is an odd function, then the integral from minus a to a f of x dx is equal to 0. I will prove these two parts. I need you to think about the meaning geometrically. Why this is equal to 0? Minus a to a f of x dx. Why this is equal to twice the integral from 0 to a f of x dx? Let us just briefly talk about this. Assume we have a function that is even. Okay? We said even, it means it is symmetric around the y-axis. It could be symmetric around the y-axis and it is above the y-axis. So this is minus a, this is a. In this case, you can see now this portion here exactly equal to this. So integrating from 0 to a is double of, integrating from minus a to a is twice the integral from what? 0 to a. Same thing if we have the function is even but it is below the x-axis, something like this. Yeah, the value will be negative, but still the integral from minus a to a is twice the quantity of the integral from 0 to a, or it is twice the quantity from minus a to 0 also. So that is geometrical meaning of the even part. What about the odd one? The odd function, if it is symmetric around the origin, you can see now the area below the x-axis will be exactly equal to the area above the x-axis. This is minus a and this is a. Of course, this is the x-axis and this is the y-axis. Similarly here, this is the x-axis and the y-axis and so on. This is x and this is y. In the odd function, this area which is above the x-axis is exactly equal to what? The area below the x-axis. And the integral, as we discussed before, it means we are adding the areas above minus the areas below, but they are the same. So the difference will be what? The difference will be 0. Okay, let us prove this. Let us prove that if we have an even function, we have twice the integral. If we have an odd function, we have the integral is equal to what? 0. Okay, the proof is not required maybe from you, but it is interesting and it will give you an idea how to prove mathematical statements. Okay, how to prove now the integral will be this. I will just do it in the margin here. Look, we have the integral from minus a to a, f of x dx. What I will do, I will split this one into two integrals from the properties we discussed before. It's equal to what? It's equal to minus a to 0 f of x dx plus the integral from 0 to a f of x dx. Okay, interesting. I will call this one I1. Sorry, this is just I. And I will call this one I1 and I will call this one I2. So our integral is the summation of I1 plus I2. I will take I1 now. Look here. What is I1? I1 is equal to the integral from minus a to 0 f of x dx. I will make a substitution. What is that substitution? I will make q equal to minus x. So what is du? Du will be what? Minus dx. Now let us change the integral now. The integral will be what? Change the boundary points. If x equal to minus a, then u will be equal to a. So if x equal to minus a, u will be equal to a. So this is a. If x equal to 0, u also will be equal to 0. What about here? It will be f of, look, f of. What is x? X is equal to minus u. And what is dx? Dx is minus du. So this is du, and I need a minus sign outside. Just give me attention now. Look, this is equal to what? From the properties we did, the integral from a to 0 multiplied by a minus, you can switch this and write it from 0 to a and remove the minus sign here. And still we have here f of minus u du. Okay, we are almost done. Look, let's go back to this. If this function is even, what happened? This is f of minus u. What is f of minus u? It will be f of u. Now we have two cases. Look, we have if it is even, okay, then I2, which I1, which is this one, will be equal to what? It will be exactly from 0 to a f of u du. And okay, I1 is 0 to a f of u du. I2 is 0 to a f of x dx. They have the same quantity. So 0 to a f of u du plus 0 to a f of u du or f of x dx, it is twice the quantity. This is if f is even. But if f is odd, what happened to I1? I1, because it is odd, I take the minus outside. So this is equal to minus the integral from 0 to a f of u du. When you take this and substitute here, you have minus integral from 0 to a f of u du plus the integral from 0 to a f of u du. So you have the same quantity minus itself, which is equal to what? Which is equal to 0. Okay, this is just a proof of the statements we wrote there. Now I will give you two exercises about these properties. The first one is a question that says, this is the first exercise, okay, and it says evaluate again the following integral. And the integral I have here is this. It is the integral from minus 1 to 1 x squared plus tangent of x all over x squared plus 1 dx. Very interesting. Okay, is this one an even function? Is it an odd function? Okay, whenever I have minus to plus, maybe I need to think about this property. Is it related to the even odd property or not? Okay, this exercise, if you take it as it is neither even nor odd. But if you use your previous studies of properties of integral, you can split this one into what? You can write it as -1 to 1. This is x squared all over x squared plus 1 dx plus the integral from -1 to 1 tangent of x divided by x squared plus 1 dx. Look again for this. You know the tangent is odd function and this is even. So the division will give you an odd function. And this is interesting. That will make life easier for us. Why? Because I'm integrating from -1 to 1 tangent of x over x squared plus 1 dx, and I claim that this is equal to 0. Why it is equal to 0? As we said, because it is an odd function, and this nice property says if it is an odd function, the integral will be what? 0. So what it remains for this part is to show that really this integrand is an odd function. And this is a good exercise for you. Show that f of x equal to tangent of x all over x squared plus 1 is what? Odd. And that is an easy exercise. You just replace x by minus x, and you know you can take the minus out the tangent and nothing will be happened here, so it is an odd function. What about this? X squared is even, and this is even, so the division also will give me even. And this is another exercise for you. You can take this and prove that it is even. Simply, you replace x by minus x, nothing will be changed. So, according to the theorem we have, or the remark we wrote here, the evaluation of this, you can write it as 2 times the integral from 0 to 1, what? X squared over x squared plus 1 dx. Now, this is the first issue you have. The second one, how to evaluate this? How to evaluate x squared over x squared plus 1. Okay, as a recommendation for you, whenever you have the degree of the numerator is greater than the degree of the denominator, try to divide and simplify. Try to divide and simplify. Okay, I will divide this, or I can also add 1 and subtract 1. It's up to you. I will divide x squared divided by x squared plus 1. This is divided by this will be 1. So that is x squared plus 1. Changing the signs, minus, minus, so we have minus 1 here. So the integrand will be written like this. 0 to 1. The quotient is 1 minus the remainder is 1 also over the divisor. That is x squared plus 1 dx. Now, you can see now we have easy integrand. We can integrate directly. So what is the answer? It is 2 times, okay, the integral of 1 is x minus the integral of 1 over x squared plus 1, or 1 plus x squared. That is tangent inverse of x. Of course, I need to evaluate this from 0 to 1. And that is equal to 2 times. Okay. If you substitute 1, this will be 1 minus tangent inverse of 1. That is by over what? Over 4. That is the first one. Minus at 0. This is 0. And this is 0. So this is equal to 0. So what is the final answer? The final answer will be 2 times 1 minus pi over 2. Okay, let me write the final answer like this. The final answer of the exercise is that. So the final answer will be equal to, as we said, it is 2 times 1 minus pi over 4, which is actually equal to 2 minus pi over 4. That is one example. You can see now this nice property simplified a lot. In first, it is cancelling one part of the integral, which is an odd function that goes to 0. And the second one, it is also simplifying the evaluation part. That is, instead of evaluating from -1 to 1, instead of substituting -1 to 1, I'm just substituting 1 at 0. That is much easier to be evaluated. What is the second example? Now let us combine the properties with it. We did some properties of integral before, and we have now a new property of integral with the even and odd functions. Okay, let us consider this nice exercise here. This exercise says like this. Look, I'm just trying to connect the properties with it before and the properties we are doing now. It says if f is an even function, So f is an even function, and we are given this. We are given that the integral from -2 to 2 of f of x dx, this is given to be equal to 4. Okay, interesting. And also, we are given that from -2 to 7 f of x dx, this is equal to 5. The question says, then find the value of, or evaluate, this integral from 0 to 7 f of x dx. Let us see now how the old properties and the new property will solve the question. Let us see what is the benefit of this word even here. We are given that from -2 to 2 f of x dx equal to 4. We are given that from -2 to 7 f of x dx equal to 5. And we are interested to find the integral from 0 to 7 f of x dx. Okay, let us look for this one first. Now, what is the integral from -2 to 7 f of x dx? I'm trying to make a link between this and this. So I will say this is exactly equal to the integral from -2 to 0 f of x dx plus what? The integral from 0 to 7 f of x dx. Interesting. Now, we have the integral from -2 to 7. We have it. This is equal to 5. We are interested to find this. We are asked to find this one. So I need to look for this. What is it equal to? -2 to 0. But I'm not giving this. I'm giving that -2 to 2 equal to 4. But I can use what now? The even property. What I can see from that, -2 to 2, -2 to 2 f of x dx equal to 4, I can say -2 to 2 f of x dx is exactly equal to, look, I can write it as 2 times the integral from 0 to 2 f of x dx, but I know also that this is equal to 2 times what? The integral from -2 to 0 f of x dx. Why? Because you can see now we have symmetry. So the integral from -a to 0 is the same as the integral from 0 to a. This is what we proved if it is an even function. So -2 to 0 is the same as 0 to 2. You can see this one easily by letting, as we did before in the proof, u equal to -x. And that's it. So what is given now? From -2 to 2, we gain it to be equal to 2 times -2 to 0 f of x dx. But this is given to be equal to what? This is given to be equal to 4. So this implies the integral from -2 to 0 f of x dx is equal to what? It's equal to 2. And that's what we need. We need -2 to 0 equal to what? -2 to 0, that's equal to 2. Now I'm replacing the values now. And this is the thing we need to find. 0 to 7 f of x dx. And we are given this. -2 to 7. -2 to 7 is equal to 5. Okay, you can now easily see that the integral from 0 to 7 f of x dx is equal to 5 minus 2. That is equal to what? That's equal to 3. Okay, let us summarize. You remember? We solve some indefinite integrals using substitution rule. We saw how the substitution rule is working over definite integrals. And now we introduce a new property of definite integral for the special functions, the even functions, and the odd functions. And we saw how to evaluate, definite integral and how this property will be used to solve some exercises related to even odd functions. That's it for substitution rule.